Hi guys, welcome back to the channel. And today I'm going to go through the TOK section of section 4.3. So I was basically going through the 4.3 section, which is about measures of central tendency, and I came across that TOK question, which is quite intriguing and fascinating at the same time. So we're just going to dive into that question set in the guide, and we'll try to make sense out of it. So I've actually written a couple of brief notes on the sheet here, and I'm just going to run you through it. So the question which is put there for us to explore is as follows. So the statement written is like this. So it tells you that mathematics can make alternate equally true formula. Okay, and what does this tell us about mathematical truth? Um, so, if you can't understand the question, if you can't process it easily, it's quite confusing when you read it. But it's not that complex if you think about it. So it's basically telling you that it's asking you, can mathematics actually create alternate equally true formula? So, and in terms of mathematical truth, so in simple terms, can we have two formula which look different but they actually convey the same mathematical truth? And to answer this question, it's not that hard actually. For example, you can have the circumference of a circle, which is pi r square, but that formula can be rewritten as 2 pi r square divided by 2, which basically becomes pi r square. So they are written in different ways, but they are actually conveying the same message. So that's a simple way of looking at it. But if you think about it in a more abstract way, it's equally fascinating. So that's what I've put on the paper here. So we all know about the formula of the area of a triangle whereby it's half time base time height. So that's the one which teachers teach in the secondary school. But there's actually a different formula called the Heron's equation, which works out the area of the triangle also. So this is the one I'm going to explore, and which is on paper here. So I've put an example for you. So you can actually have a triangle having length 7, 8, and 9. And if you want to find the area of that triangle, you can actually calculate something called the semi-perimeter, where you add all the sides and you divide by 2. You get 12. And then that number 12, you can actually fit it in the Heron's formula, um, which is here. So the number 12 gets put here. And then you take the 12, it's all under a square root. So the 12 is multiplied to the semi-perimeter subtracted from each length, so from the length of each side, and multiply to each other. So you basically have the semi-perimeter subtracted to each side, multiply, so it's a product of that, multiply to the semi-perimeter, and then you square root that. So if you use the Heron's formula, you end up getting root of 720, which is 26.83. Okay, and that's the formula which people don't learn in secondary school because it's not used. What you're used to is the half time base time height, which I've written down in on this page here. So we are used to a is equal to half time base time height. All right, which is half the area of a rectangle, because a rectangle is base time height. To get a triangle, you cut the rectangle in a diagonal manner, and that becomes half times the rectangle, so half time base time height. So if we rearrange that equation so that we can work out the height, so I'll need to move the divide by 2 there. It becomes times 2, so 2a, and then you move the base to the other side, becomes divide by base. So if you need to make Heisenberg formula, you need to send the 2, which becomes 2 times a. You send the times base, which becomes divide by base. You end up getting that equation. Height is 2a over the base, And if you take the base as number 7, because we had 7, 8, and 9, and you can actually do that with any number. But if I take the base as 7, you get the height as 2 times 26.83 divided by 7. All right. And the 26.83, it was here, the area, okay, from the previous section. So you end up getting 7.66. So that's the height. And then if you use the formula, A is half times base times height, so half times 7, which we took as base, and height 7.66, we end up getting 26.83, which is the same answer. Okay, so we had two different formula giving us the same answer. Okay, so this is what happened, and obviously the first one is not that used, so you probably didn't know about that, but it's quite an interesting thing to notice that you have two different methods, uh, but you end up getting the same answer, so the same truth. So, what are the different conclusions we can draw from that small experiment? Um, the first one, which is quite glaring, is that the truth is the truth. So you can use any method as long as it's logical and it's structured, it makes sense. So whatever steps you're doing, the steps are actually mathematically correct, then it will lead to the same answer. So the truth is universal. All right, so that's what the math also is telling us, and that's something which is quite common in real life also. The truth is universal. You can actually take any path, it should lead you to the same truth if the truth is really true. Okay, so that's where the TOK part comes into place. Um, but what I would like to emphasize is that in the first example, where we explored the Heron's equation, to use that equation, you need to have all the three sides. Okay, if you don't have all the three sides, we can't use the equation, because in step one, you're actually adding all the sides. So unlike the classical triangle equation, whereby you can use Sukatwa and find different sides and then use the area of the triangle, we can't actually do that with the Heron's equation. So context is very important, and that's one of the points I've written down here. So the math truth is context driven. Okay, meaning we need to look at the context and then decide which equation we're going to use. Okay, so the Heron's equation works if we have all the three sides. With the half-time base time height, you can actually use other methods, and you just need two different lengths to actually work out the area of the triangle. What's the second truth which comes up here? So math solving is consistent under the same conditions. What does that mean? So you can basically use the Heron's equation with any triangle whereby all the three sides are known. So if the numbers change, you can still use the equation. So a context where three sides are given, you can always use the Heron's equation. So the solving is consistent because it's under the same condition. What's the condition? You have three sides given. And with the second equation also, if you have the base and the height, no matter what the base is, what the height is, you should be able to use the formula. So the solving is consistent under the same conditions. If you keep the conditions the same, the formula always works. And the third mathematical truth which we got out from this experiment is that flexibility and adaptability in problem solving is important. Once again, going back to the same discussion with the Heron's equation context, if we have three sides, how do we adapt to that situation? We use the Heron's equation because it takes as input three sides. If we have two sides given to us, we adapt to the situation. We can't use the Heron's now, and then we use half-time based on height. And it's the same kind of scenario with most formula in math, because if you look at the sine rule and the cosine rule, for example, in trigonometry, if you have three sides given and one angle involved in the equation, you always use the cosine rule. If you have two sides and two angles given, you always use the sine rule. So you adapt based on what's given to you. So these are the three truths which I get from this context. So if we try to wrap it up, and I tried to answer this question. So mathematics can make alternate equally true formula. Yeah, we just proved that. What does does this tell us about the truth? We came up with three key things, okay, which we went through in the video. All right. So I think that was interesting to explore. I hope to see you next time for another TOK topic.